Welcome to STT 315 Recitation 4. We're going to go over the recitation activity along with homework 1. So first, consider a variable z which has the standard normal distribution. So its probability density function, or PDF, is 1 over the square root of 2 pi times e to the negative z squared over 2. And here is a histogram of what the PDF looks like. So first, part A wants us to find the mean of this variable. So for standard normal, the mean is 0, and the variance is 1. So, or standard deviation is 1. So you can find that by integrating this probability density function with respect to the variable z. And note that phi of z, this density function, is an odd function when you're integrating it. And you'll also notice that the histogram is centered around 0, so the mean is 0. And I'm also going to show you how to do this through R as well. So then it'll ask for the medium, lower quartile, and upper quartile. So I'm going to transition to R right now, actually, to kind of show you how to do this. So to find the median, which is also known as quartile 2, you can do the function q norm of 0.5 or 1/2. So that is, when you run that, that is equal to 0. We get q2 equals to 0. And also, you'll notice that the mean is also 0. I know this isn't a perfect 0, but this is because R generates like a random distribution, so it's not always perfectly 0 in R. But standard normal means that the mean is 0. But anyways, okay, so the median is 0, and you can do q norm of 0.25. Sorry, q norm of 0.5, and that will give you q2, so here. And then q1, quartile 1, is, or also known as the lower quartile. You can do q norm 0.25, and that'll give you negative 0.6744898. So I'm going to label that q1 for the lower quartile, and then q3 is the upper quartile, and you can calculate that by doing q norm of 0.75, and that'll give you 0.6744898. So notice that since q norm uses a standard normal distribution where the mean is 0, you'll notice that it's a symmetric distribution. It's symmetric around 0, which is the mean. And so quartile 1 and quartile 3, since it's centered around 0, the magnitude is the same, but you'll notice that quartile 1 would be on the negative side of 0, so that would be like right here, and quartile 3 would be over here. And since 0 is in the center, this is the magnitude would be the same, so we have the 0.6744898. All right, so that's just an observation to note, because that is due to being centered around 0, to being symmetric. All right, so next we're asked for the interquartile range in part E. So that's quartile 3 minus quartile 1. So you do Q norm 0.75 minus Q norm 0.25, and that'll give us the interquartile range of 1.34898. Next, we want to find the right whisker, which is quartile 3 plus 1.5 times the interquartile range. And then we'll also find the left whisker, but first let's do the right whisker. So the right whisker, R, as I labeled it, is 2.697959. And the left, you would do Q1, or the lower quartile, minus 1.5 times the interquartile range. And that gives us negative 2.697959. Okay, so notice too that the magnitude of the left whisker versus the right whisker, so that would be the same length, but one is negative and one is positive because we're centered around 0. Okay, so now the next task is to draw a box plot. So just to recap, we have our median, so our mean is 0. Our median is 0. Our lower quartile is negative 0.67. Our upper quartile is positive 0.67. Our interquartile range is 1.34898. Our right whisker is 2.697959. And our left whisker, this should be negative. I forgot to write the negative, but negative 2.697959. Okay, so next we're going to draw a box plot. So in R, you can do this by defining Z as our random variable Z as R norm, and we'll take 1,000 sample points. And then we're going to use the box plot function, and we'll take the box plot of Z, our random variable, which follows a normal distribution, and then we'll say horizontal is true. So that way our box plot looks horizontal. So when you plot that, that's right here. That's right here. You'll get this plot over here in RStudio. And I'm gonna transition here real fast because I labeled the different parts of a box plot. So RStudio will give you something that looks like this. And so just to recap, here these circles are your outliers. Here is your left whisker, and your right whisker are the green lines that extend from the boxes. And then we have our Q1 is the first vertical line of the box. Q2 is the middle line of the box, or also Q2 equals the median. And then quartile 3 is the third horizontal line of the box. And our interquartile range is Q3 minus Q1. So it's this distance, the red distance. All right. And if you compare our answers, what we had got for parts A through G, it should match this plot. So we had that our median is 0. So notice that our median and Q2 line up with 0. That our lower quartile is negative 0.674. So that is around negative. If we draw the line from Q1 down, here is around negative 0.674. And then since it's symmetric, this would be around positive 0.674. And then our range, so this distance here is 1.34. So if we look on the number line, okay, that matches, or 1.35 if you round. And then the right whisker is 2.6979, and then same for the left whisker, but negative 2.7 if we round, and that length matches what we got. Okay. Next, we need to find the proportion of outliers. So to do that, we're going to take the probability that our z random variable is less than or equal to the left whisker, plus the probability that our random variable is greater than the right whisker. So in this situation, if it's less than the left whisker and greater than the right whisker, we're talking about this area here, less than the left whisker and greater than the right whisker. So if we add those two together, we should get the total number of outliers. So here, we'll take the p norm of L plus 1 minus the p norm of R. And this will give us 0.007. So I'll show you in R. So if you do here, that calculation, it'll give you 0.0069766603, but when you round, you get 0.007. So, and that means that about, so that's about 7/10%, or about 7 outliers in a sample of 1,000. And the reason why I'm saying out of 1,000 is because we set up our z to be out of 1,000 like data points. Okay. Now we are moving on to number 2. So yes, we covered all of this. So this is all of the code that I used for question 1, and now we're moving on to question 2. So we're going to consider the variable age from the nutrition study data frame. So to set it up in R, we're going to name our object age and have that equal to the nutrition $age, which is the column of our Excel sheet, our age column of that data set. And so then we want to find the size of the data. So we want to find the length of that column. So how I found it was I went to my files and I store my data in stat315. So once I find my file name here, which your route might be a little bit different, your location where you store your stat315 data, you can hit import data set before you start running your code. And when you import data set here, this age variable right here, oh, I can't highlight a thing, a column, but this column here is the column we're using. So we want to find the length of this, which you can code it in R, but if I scroll down to the very bottom, we can see that our total length is 315. So there's 315 people. That's our sample size, is 315. All right, so now let's go to here, I'm gonna just run the question 2 section right now. Well, I guess I could run it line by line. Okay, so age, and then I'm gonna say n is our length. So if I want to know, okay, what is n? Our length is 315, which is what we would expect. So that's 315. So now we want to find the mean. So we can use the function mean. So if I label m as my mean. What is M? 50.14603. Okay, and then we want to find the median. So that also is a function in R. So if I do median age, and then, sorry, where am I? Okay, so median age, I ran that. What is our median? We'll get that our median is 48. Now we want to compare, part C, we want to compare our mean and our median. So if our mean is 50.146 and our median is 48, our mean is larger than our median. Next, we want to draw a plot of the relative frequency curve of age. So we're going to make a histogram, and then we're also going to have the line follow the density of the curve. So when we do that, run. So here's the plot that we're going to get. And so you'll notice that this histogram where the bar graph, the histogram, is our our sample. So if we go through our sample and we were to put in our bucket, okay, from 20 to 25, we have this many of our data points fall in this age range, and so on and so forth, and we construct our histogram like that. This curve shows the density of our histogram. And the next question asks for us to relate the skewness of the age distribution. So here we would have a positive skew because our mean is greater than our median. So if we look back at our graph here, we're skewed, we have a positive skew, or we're skewed to the right. So that's because our mean is greater than our median. If it was the other way around, where our mean was less than the median, then we would have a negative skew, or it would be skewed to the left. And if our median pretty much equaled our mean, then it would be symmetric. There wouldn't really be a skew if our mean equaled our median. But in this case, our mean is greater than our median, so we have a positive skew. All right, now the distribution of age is bimodal. So here we have two humps to our graph. If it was unimodal, there would just be one. It would be like a bell curve. And if it was trimodal, then there would be 3 bumps, but there's only 2. So in this case, it's bimodal. Okay, next we have to find our different quartiles. So quartile 1, quartile 2, and quartile 3. So in R, you can use the quantile function. So when you run that, you should get, it lists the 0%, 25%, 50%, 75%, and 100. So we're interested in these middle 3, the 25, 50%, and 75%. So 25% quantile is the first quartile, which is 39. Our quartile 2 is 48, and our quartile 3 is 62.5. So that's what I have written here. And then our interquartile range is quartile 3 minus quartile 1, which would be 62.5 minus 39, and that would give us 23.5. And then next we have to draw a box plot. So if I draw a box plot, I did it two ways so you can see. So first I did box plot of our age and I did horizontal false. So that means that it'll produce a vertical box plot because horizontal is false, so vertical would be true in other words. But if you do horizontal equals true, then you have a horizontal box plot. So I prefer looking at the horizontal one, but it's really up to your preference unless if the professor ever wants to like make that distinction in a certain assignment or something like that. All right, so this is what our box plot looks like, and I'm going to transition to this screen because I labeled them. So here we have our quartile 1 is our blue, quartile 2 is green, or the median equals quartile 2, so our median is green, and then quartile 3 is red. And previously we had that 39 was quartile 1, 48 was quartile 2, and 62.5 was quartile 3, and that lines up with where our ages line up if you were to extend this to see, okay, where does it actually line up? And then our interquartile range is Q3 minus Q1, which is 23.5. So on this number line, it's roughly 23.5. Okay. The distance is roughly 23.5. All right. Question 3. The distribution IQ among elementary school children has the normal distribution with mean 100 and standard deviation of 16. So we're going to hold on to this information for the next few tasks. So part A, what proportion of children have an IQ of at least 105? So the probability of X greater than or equal to 105. So notice that it says at least. So that's our key word. If it's at least 105, then it's 105 or more than 105. So that's why we did X greater than or equal to 105. And that equals 1 minus the P norm of 105. And then notice that we have the mean is 100 and then 16 is our standard deviation. So when you put that into R, you get 0.3. So I did 1 minus P norm 105, 116, and you get 0.3773303 right here. And then part B is what proportion have an IQ between 80 and 110. So here we have 80 is our lower bound and 110 is our upper bound, and we want to know what is the probability that X will fall in between 80 and 110. So we're going to do P norm of 110, which is our upper bound, and then this is our mean and our standard deviation, and we're going to subtract it from the lower bound, which is the 80, 100 is our mean, and standard deviation is 16. So when you do that in R, you can just plug it in, and you'll get 0.628367. So that is our proportion that have an IQ between 80 and 110. And then part C. So to be a member of Mensa or MENSA, one must be at least at the 98th percentile. What is the minimum IQ for membership to Mensa? So here, we know that our mean is 100, and we know our standard deviation is still 16. So the number that should go here is the percentile that we're dealing with. So in this case, it's the 98th percentile, so that would go here, 0.98. And when you run that in R, you get 132.86. So that's the minimum IQ to be a member, is 132.86. Okay. Now we're dealing with our homework. So homework 1, now notice on Long Kappa that your numbers that you're dealing with are randomized per, like, every student will have different numbers than what I'm dealing with, but the methods that I'm using to solve the questions will be the same. So your numbers at the end will probably not match mine, but you want to make sure the steps that I'm taking are the same whenever we have like specific numbers that we're dealing with. So question 1 is to find the 60th percentile of the data below. So your homework question may be the 49th percentile or the 62nd percentile or something that might change. So this is the data that I was given. So there's 2 ways to do this. You can either do it in R or I also kind of did it by hand just to get a sense of, okay, what it would be. So first, let me show you how I did it in R. So in R, I let X equal this set of points, which is what I was given. And then I could sort them from smallest to largest. And then I wanted the 60th percentile, so I did the quantile function. And so X, which is what I labeled my data, would be the object that I put in. And then the second thing the function calls for is the percentile that I'm interested in, so it would be the 60th percentile. So when I do this function, I get 15. So the answer is 15. Now, if I wanted to do it somewhat like by hand, the way I would think through it is, so I have 9, I would count up the total that I have. So I have 9 different data points in my sample. And then I want to know, okay, once they're sorted, I want to know where 60% of 9 kind of fall in. So I would do 0.6 times 9, and that gives me 5.4. So then from there, I would count from the smallest to largest, because we work from left to right. See where like 5.4 would lie. So that would be 1, 2, 3, 4, 5. So it's somewhere in between here, which is 15, because the 5th is 15 and the 6th number is 15. So it would also be 15. So that would also give me an idea of, okay, what the 60th percentile would be. But when I found the exact solution, it was just easier to do it by R. But this just gives you an understanding of, okay, where the 60th percentile would fall. It would fall somewhere over here. Okay, the next question that I had is, if a population has a median income of 38,000, then what percentage of the population has income less than 38,000? So since it's the median income is 38,000, then the median means that half of the data falls under 38,000 and half of the data is larger than 38,000. So the percentage of the population that has income less than 38,000 would be half. Now, let's say if the question said, if a population has like, let's say if it was like quartile 1 was 38,000, then the percentage of the population that has income less than that would be 25% if it was quartile 1. Or it would, and 75% of that population has over 38% if we were dealing with quartile 1, for example. But the median is half and half. Okay, the next question. A statistics department consisting of 35 faculty has a median salary of $53,000. One of the senior faculty with a salary of $69,000 retired from the department and was replaced by a new faculty with a salary of $71,000. What can you say about the median salary of the current faculty? So here we can say that the median will remain unchanged because, let's see, the median is 53,000 and a senior faculty, so previously, someone had 69,000 and then was replaced by 71,000. But notice that 69,000 is already greater than the median. And then when this guy left and the new person was replaced, it was still greater than the median. So when you know, if you were to cross off one from the, one from the bottom, one from the top, and eventually work your way to the middle, that middle number wouldn't change because the previous number and the new number are both larger than the median. Okay, question 4 is to find the average of the 12 numbers below. So to find the average or the mean, you're going to add up all the numbers and divide it by the total number of numbers. So 17 plus 18 plus 11 plus 7 plus 14 plus 7 plus 4 plus 7 plus 18 plus 1 plus 20 plus 13 divided by 12 will give us 11.42. So your numbers may be a little different, and your total numbers may be different. So the total number of numbers would go in the denominator. Okay, question 5. So to find the average of the following 27 consecutive numbers. So we want to do the average of 17, 18, 19, 20, 21, all the way to 43. So I did this in R because it was pretty easy to type. But when you add all of them together, I got 810. And then 17 plus 18, all of these numbers are 20. There's 27 total numbers or 27 data points. So to find the mean, you would do 810 divided by 27, and that'll give us 30. So that is the average. On to question 6. So 5 students were given a test. The average and standard deviation of the 5 scores were found to be 58.2 and 22 respectively. So notice that 5 is our sample size, 58.2 is our average, and 22 is our standard deviation. Later, the instructor found out that he had made an error in one of the problems and decided to add 2 points to each score. The mean and standard deviation of the new scores are. So if the instructor adds 2 points to every score, notice that every is the key word here. the standard deviation will not change. Because if every score is being added, the spread in the data won't change. And however, the average will change. The average will increase because if 2 points are added to every score, then the numerator of when you average them all together. So let's say this was our data set, even though it's not, just for explanation purposes. If we were to add 2 to every number here, our mean would actually increase because our numerator is getting bigger. So we want to find the option where the mean goes up, but the standard deviation is the same. So here we want a standard deviation of 22, so that leaves this option and this option. And then we want a larger number than 58.2, so that would be 60.2. So here this would be our correct option because we can cancel this option here. Next is question 7. So an instructor calculated the average score and the sample standard deviation S of the scores of his class and used the following grading scale. So you get an A if at least 2 standard deviations above the mean. You'll get a B if you're between 1 and 2 standard deviations above the mean. You'll get a C within 1 standard deviation of the mean. And you'll get a D if you're below 1 standard deviation of the mean. When the grades were announced, the students were unhappy, and he proposed the following alternative. Add 10 points to each student again, calculate the mean and standard deviation for the new scores, and then follow the same scheme. Do you think this scheme will improve the grades? So no, the scheme won't improve the grades because the standard deviation will not change. Here, notice that the key word is each. So since 10 points will be added to each of the students' grades. So here, because the scores are all determined based off of standard deviation, the grades won't improve at all. However, if the grades were determined, not based off the standard deviation, but just on the mean, then things might improve, depending on, the mean would increase in that situation, depending on how his, what the new grading scale would be. But with this grading scale, the standard deviation will not change, so the grades will not improve. They'll actually stay the same. All right. So here we have a histogram. So data were collected on the lead levels of children of battery factory workers. The data are displayed in the histogram above. Choose the correct answer. So C here is the correct answer. There are 33 excuse me, 33 children in the data set. So how I did that was I just see how many data points are in each bucket, and then I add all that together. So here this would be 8 are from 10 to 20 range, and then 7, and then 10, and then 6, and then 1, and then 1. So when you add that together, you get 33. But now let's look at the other incorrect answers, and I'll explain why those are incorrect. So the first part, so what I labeled A as the median lead level, the level that exactly half the children exceed, is less than 30. So the median lead level actually equals 30, because if I were to cross off the lows, cross off the highs, and so on and so forth, and find that middle number. So let's say if I cross off this 8 and then I could cross off this 8 because 6 plus 1 plus 1 is 8. Then I'm between here. And if I were to cross off 7 from here and cross off 7 from here, there would still be 3 that are in this 30 to 40 range. So our median lead level actually equals, somewhere between 30 and 40. It's definitely not less than 30. So that's why I can cross off A as incorrect. B is the maximum lead level is less than 60. So this is incorrect because we have values that are greater than 60. So we have one value that's in between 60 and 70, and one value that's in between 70 and 80. So we can eliminate B. And then D, none of the answers is true. We can eliminate that because we already found that C is true, that there are actually 33 children in the data set. Okay. Question 9. The histogram corresponding to the above box plot is it skewed or is it symmetric? And which way is it skewed? So this is a vertical box plot, so I can tell it's skewed to the right. If I wanted to take this and make it a horizontal box plot, so if I have 0, I didn't write the whole number line, and then 25 here. If this were a horizontal box plot, it would look something like this. So we can see here that it's not symmetric. It's definitely skewed to the right. And if I were to also take this box plot and visualize it as a histogram, we would get something that looks like this. So that you can see clearly is skewed to the right. All right, so we have gone over homework 1 and the recitation 4 activity. I hope this was helpful. Bye.